Hello, my name is Zach Sims. I'm an aerospace engineering graduate student at the University of Illinois, and this is my presentation on ablative nose tips for reentry vehicles. There are currently two reentry vehicles in the United States Air Force arsenal. They're active on the Minuteman III intercontinental ballistic missile. There's the Mark 12A and the Mark 21. The picture on the left here is the reentry for three Mark 12A vehicles over the Kwajalein Atoll in the Marshall Islands. These vehicles travel about 4,200 miles in under 30 minutes when we do our test flights. They leave from California. They arrive in the Marshall Islands about 30 minutes later. The flight conditions that they encounter while they're re-entering the atmosphere are pretty harsh. The initial reentry velocities upon reentry are typically around 17,500 miles per hour, or approximately Mach 23. They can experience accelerations during reentry of more than 50 Gs. And at these velocities, the temperatures on the surface can be in the 4,000 to 6,000 Kelvin range. At these temperatures, nitrogen and oxygen dissociate. The diatomic molecules that we're used to seeing of nitrogen and oxygen can break apart, and we get individual nitrogen and oxygen atoms as part of the environment. The air can also ionize. The electrons leave the molecules, and we also see radiation effects from the atomic nitrogen and oxygen. So when a vehicle is experiencing these environments, we need a good thermal protection system that needs to be designed to withstand this atmosphere or this environment. So what we typically use are ablative thermal protection systems. These ablative TPSs have good behaviors for high heat flux. They're good for short periods of time. The leading edge material is sacrificial because these vehicles are designed for single use. The design has to include sufficient material as well, sufficient thickness for weather encounters and the time spent in the atmosphere. When you're flying through clouds or ice particles or snow, that erodes or ablates your nose tip more quickly. So you need enough material there so you don't end up hitting the actual structure itself. So how does ablation work? How does it provide thermal protection? The outer surface chars and sublimes. It goes straight from solid phase to gas. Then the inner material underneath the char layer experiences pyrolysis and creates what's called the blowing effect. This blowing effect creates blockage against convective heat flux, and the charred and vaporized material inside the shock layer interact and create blockage against the radiative heat flux. And don't worry, we're going to be talking about these in the next few slides. So pyrolysis. Pyrolysis is the thermal decomposition of materials at elevated temperatures in an inert atmosphere. Basically, your carbon materials break up, they turn into gas, and they are free to mix with the atmospheric nitrogen, oxygen, and hydrogen that has been broken up. And so they create these carbon clusters or hydrocarbons or carbon oxides. And so you've got a bunch of these gases floating around inside the boundary layer, inside the shock layer, around the outside of your vehicle. And these gases, the interactions, protect the vehicle from radiative and convective heat transfer. So convection blockage is very similar to transpiration. So in transpiration, a coolant is injected into the flow, and this coolant comes out and it creates a protective barrier between your hot boundary layer and your surface. So in an ablative thermal protection system, the pyrolysis products, these carbon-based gases, um, act as the coolant. They create a protective film between the harsh outer environment and your vehicle. In terms of radiation blockage, radiation typically comes from atomic nitrogen and oxygen in Earth's atmosphere, and this occurs at temperatures above 3,500 Kelvin. So the pyrolysis gases, the carbon clusters, hydrocarbons, and carbon oxides we've been talking about, they each have a set of spectral modes at which they can vibrate. Some radiation emissions have similar wavelengths to the carbon gases spectral modes. And so that means that when the radiation hits a molecule at a wavelength close to a gas's spectral mode, the molecule can either absorb the radiation or re-radiate it in a different direction, directing the heat away from the material surface. Um, and so, for example, a C3 molecule has a spectral mode around 160 nanometers. Nitrogen has an emission line at 174.29 nanometers. And these wavelengths are actually close enough for carbon to absorb the radiative heating coming from the nitrogen atoms. So any radiation from this nitrogen gets absorbed by the carbon and doesn't make it to the vehicle surface, keeping the vehicle cool. So some of the materials that have been experimented with to make up an RV nose tip they started with carbon phenolic, but they found that carbon phenolic ablates rapidly and is unpredictable. When you get asymmetric nose tip ablation, that adds extra aerodynamic forces to your vehicle, and that can create inaccuracies. They also found that the carbon phenolic is subject to mechanical failures at high temperatures. It can get brittle and large chunks can break off, and that's not good either. So they moved on from carbon phenolic to graphite. They found that graphite ablates more slowly and evenly, which is good, but it can also be subject to mechanical failures at high temperatures. It can also be a little bit brittle. So the next step from graphite was 3D woven carbon. They found that this ablates slowly and evenly, and it doesn't have any mechanical issues at high temperatures, but occasionally there were issues with asymmetric ablation. So to help that, some studies were performed where tungsten inserts were put into the nose tip. Tungsten resists heat and ablation. It helps the nose tip maintain a predictable shape and is overall good for ablation and thermal protection. Some other materials that have been studied and applied on former reentry vehicles were Teflon and carbon fine weave pierced fabric. So a quick summary, reentry vehicles experience very harsh environments during reentry. And so they undergo ablation, which is a complex multidisciplinary topic of study. It's chemistry, it's heat transfer, it's material science, it's a little bit of everything. And the ablation of these carbon materials can protect your vehicle body by performing radiation blockage and convection cooling through pyrolysis and charring. The RV nose tip materials must be specially designed to help with aerodynamics, to help with this ablation, and they need to meet all of these requirements to help your vehicles get where they're going safe and sound and nice and accurate. So this page lists some of the references that were used in compiling this presentation, lots of pictures and graphics and good information on ablation. Thanks.